This example is basically an overall complete example that could be like one of the ones from the combined loading project. We have a steel tube with an outer diameter of 2 inches and a wall thickness of 1/4 inch rigidly attached by a flange to the wall, and we have a 500 pound force being applied at the hook. So the problem asks us to draw the inner circle for the critical state of stress. We know that the yield strength of the material is 60,000 psi. We want a factor of safety using our maximum shear and our von Mises criteria. All dimensions are given in inches. So we know that we're going to have to calculate the stresses based on the loading, which means we need a few geometric properties. Moment of inertia. Again, this is our section of interest. So we were told that the outer diameter is 4. Our wall thickness is 1/4 inch, so the inner diameter is 1.5. So our modulus, our moment of inertia, 0.5369. We know that the polar moment is twice that. .07 inches to the 4th. And we have to think about what are the stress resultants, where is our worst case scenario, and what are the values of these. It is point A that we're looking at, back at the connection point of this cantilevered pipe. And so what do we have going on? Stress resultants at A. So we've got our circular cross section, and we know that we will have a shear force in the same direction as the applied. We know we will have a bending moment tending to make the tip deflect downward that would have this moment arm this way of 15 inches. So we have an applied force of 500 pounds times the 15-inch moment arm, so 7,500 inch-pounds. And then we also have a torque that would be represented as along the axis in the clockwise direction, with the moment arm in this direction, that is the 500 pounds times the 9-inch distance gives us a torque of 4,500 inch-pounds. Now, how does that relate to stresses? So, the stress resultants at the connection of the cantilever end up creating several stresses at that connection point A. We have from bending, it's going to generate tension at the top, compression at the bottom, and the magnitude of that is given by normal stress sigma plus or minus mc over I. We figured out that the bending moment magnitude is 7,500 inch-pounds. The distance from the neutral axis of the structure to the top, we know that it's a 2-inch outer diameter, so it's a 1-inch distance, and we figured out our moment of inertia earlier, 5,369 inches to the fourth. So we have a plus or minus 13,969 psi normal stress from bending. From our torque T, we know that the shear stress is Tc over J, the applied torque, times the distance from the neutral axis to the outer surface, divided by the polar moment of inertia. We have our 4,500 inch-pounds of torque, the same distance from the center to the neutral axis, and our polar moment of inertia, 1.0738 inches to the fourth. So we have a shear stress value of 4191 psi. Our third, from the shear V, we know that the shear stress from a shear load is 0 at the top and the bottom of the section where the normal stress is magnitude, where the normal stress is maximum, where sigma is max. So we ignore the shear stress. So this ends up with a stress state if we have our section of material we have looking at the top, so this is section at top of pipe, we would have a normal stress in the x direction along the pipe of 13,969. We have a sigma y of 0, and we have clockwise shear stress everywhere. We have tau xy of 4191. So we can translate that into our stress state drawn in 2 dimensions. Of 13,969. Sigma y equals 0, and a tau of 4191. Now, to draw more a circle with this stress state, we need axes. We know this time that sigma y is 0 and sigma x is positive, so we will skew our axes to the positive normal stress side. And we know that this is our sigma axis, this is our plus tau. And the first point that we plot is sigma x tau xy. So we need positive 13,000 and positive 4,000. So that's our point 1. Our point 2 is sigma y and minus tau xy. Our sigma y is 0, and our shear stress is 4191, so we go to here, we connect our points with a line, and we add our circle. We add our circle with no fill, and we know that this location is our sigma average. We know this location is our sigma A. We know that this location is our sigma B. And we can calculate those values, that our average is sigma x plus sigma y divided by 2. So 13,969 plus 0 divided by 2, which gives us sigma average of 6985. 6985. We need our radius is the half of the difference squared and the shear squared. So 13,969 minus 0 over 2 squared and 4191 squared. All of that square root. The radius is 8145 psi. And just noting all of these points on our Moore's circle. To emphasize, this is sigma x and the shear. This point is sigma y and the minus shear. This distance is the radius. So sigma A is the average plus the radius. Sigma B is the average minus the radius. Coming back over to get values for those. Sigma A, 6985 plus 8145. $15130. The second principal stress, sigma average minus the radius, 6985 minus 8145. So sigma B is minus 1161. So noting those locations over on our Moore's circle, we'll put those in blue. This value, 15130. This value, minus 1161. Okay, that gives us our principal stresses. We know that in this case of plane stress, we know that our third principal stress, our sigma C, is 0. Now, moving on to our failure criteria. So, failure criteria. We were first asked for the max shear. Failure criteria, which is defined as factor of safety is the yield strength of the material over 2 times that maximum shear, where the maximum shear is sigma 1 minus sigma 3 over 2. Well, we have sigma A, sigma B, and sigma C of 15,130 minus 1161 and 0. We need to rank and reorder these. 15130, 0, and minus 1161, so that we then see that our max shear is 15130 minus a minus 1161 over 2, or 8145. Now we can put that into our max shear criteria, factor of safety. The strength of this material was given as 60,000. So 60,000 over 2 is 8145, ends up being 3.68. All right. For the other criterion, distortion energy criterion, or von Mises, distortion energy, or von Mises, we have to calculate the von Mises equivalent stress, meaning our sigma prime, and we're going to look back and use our sigma x, our principal, or our original stress state in the xy coordinate system. We know that sigma y is 0, so our von Mises equation simplifies to the square of the normal stress in the x direction plus 3 times the shear stress squared. So that is our 13,969 squared plus 3 times 4191 squared is 15,743 for our von Mises equivalent stress. Factor of safety for von Mises is the yield strength, tensile yield strength of the material over the von Mises equivalent. So again, our 60,000 divided by the von Mises equivalent, 15,743, is 3.81. So to compare the two, we have 3.68 according to our maximum shear stress failure criteria, and we have 3.81 for our von Mises or distortion energy criteria, showing there is a slight difference with the shear stress one being slightly more conservative.